Well, good afternoon. It's a bit late. I had a phone call while I was trying to finish lunch, an advising question, and I finally said, look, I've got class coming up. I've got to go back. And then when I got here, I also had two students taking makeup tests. So I've been dealing with that a little bit. And so sorry I'm a little late getting started here. But there's nobody else in the classroom. It's supposed to be Cal 3, class starting at 2:15. It's already 12:15. It's already 12:25 or 12:26 now. So sorry about getting started late, but since no one's in the room, let me go over just a couple of not new announcements, but just to let you know what's going on in case you're trying to get in touch with me. There's some office hour adjustments coming up and then permanent changes coming up. First, tomorrow, on Tuesdays and Thursdays, for the first mini-term, which is ending this week, my office hours have been 11:15 to 1:15. But not tomorrow, because tomorrow I'm taking my physical science class on a field trip. So I've got to, as soon as I get out of my class that ends at around 11:15, I've got to book it over to the Birmingham campus as soon as I can in order to get a vehicle to transport some of the students to the field trip. So therefore I won't be in the office from 11:15. I probably won't be back even at 12:15. It's probably going to be closer to 12:30. So my office hours tomorrow will be 12:30 till, or somewhere around 12:30, plus or minus 12:30, until just before 1:15. At 1:15 we've got to leave in order to get to the field trip on time. So limited tomorrow. Now while I'm on this, let me just tell you this. This is the end of the first mini-term, which means we're at midterm this weekend. That's the middle of the term, sometime this weekend. So if you are in a first mini-term class, the student course evaluations are currently open. And please do your student course evaluations as soon as you can on the first mini-term classes. So that's that. Secondly, they periodically ask for, they're supposed to ask every term for midterm progress reports. That means I need to have a grade from everybody. And right now I have one paper turned in and two first tests turned in. And I'm ready to give you the second test today, but nobody's here for me to give it to you. So I really need some sort of grade in, if possible, next week, okay? So then I'll be able to do midterm progress reports, either your research paper or your first test. Okay, there's that done. All right, I covered Thursday. Friday, I may have a little bit of adjustment to my office hours then. I don't know for sure. We've got to go out of town this weekend, and there's something coming up on Friday evening. We don't know exactly what time that is, and we've got to leave in time to get there. If it's late, I can leave my regular time. If it's earlier in the afternoon or evening, then I'm going to have to leave campus a little early. So normally my office hours on Friday are 8 to 12. However, I might need to leave a little before 12. Usually I'm here well after 12, but tomorrow I won't be able to be after 12 and may actually have to leave, on Friday, may actually have to leave before 12. Okay? So that's Friday. Next week, again on Tuesday, normally I have office hours starting at 11:15. 11:15. However, on Tuesday I have a doctor's appointment at 10:40. So that means I probably won't get out of the doctor's office before 11, if that early, okay? And then driving back here will be, I doubt if I'll be here by 11:45. So don't expect me in my office 11:15. It'll be more likely on the order of 11:45. Now, to make up for that, and this will be a change for the second mini-term, I'm ending my physical science first one class tomorrow. Last day is tomorrow. That's the field trip. And then some of them are coming back to take their last test and final exam. So that'll end that class. But on Tuesday, I start Physical Science 2, but that class starts later. Some of the automotive students have to have that, and they don't get out of their block. They have block scheduling, and they have one class that goes from 1 to 3. So they can't get over here before 3:15. So therefore, the second mini-term physical science class starts at 3:15 and goes until 7:45 in the evening, because it's a 2.5-hour class, a 2-hour lab. So that means that beginning next week, my normal office hours will be 11:15 on Tuesdays and Thursdays, 11:15 till 3:15, full 4 hours of office hours. Of course, I eat lunch sometime in there, probably 12 to 1 approximately. But on Tuesday, it will be later than that, because I probably won't be back from the doctor's office any earlier than, what did I say, 11:45? Yeah, 11:45 would probably be the earliest I get back, and it may even be later. But then I'll be in the office until 3:15, and then for the rest of the term, it'll be 11:15 to 3:15 on Tuesday, Thursdays. So that's pretty much all the announcements I have. I would ask if there are any questions, but there's no one in the room to ask that. So let's move on to, I'm trying to find where we left off last time. And yeah, we did example 3, but there is example 4 is where we're starting today. However, that's not on the slide set. Now, to see a interactive version of this type of an example, and it may even be this one exactly, you can go to larsoncalculus.com and see example 4 or something like example 4 worked out. And what it's asking is for the hyperbolic paraboloid. Let me get my pen set up. Okay, here's a hyperbolic paraboloid. Z is equal to y squared minus x squared. Okay, now, why that is called a hyperbolic paraboloid, if you remember back from, I believe it was 11.6 or something like that, we did the quadratic surfaces. Okay, for z equal to a constant, I was going to say, yeah, well, z equals 0, you'll find there's no value except x equals 0, y is equal to 0, okay? The origin will be where z is equal to 0. That's the only, let's see, is it the only possible value? Well, not quite. When x is equal to y, or x equal plus or minus y, and y equal plus or minus x, those would all be zeros. So if you look at in your text, you'll see the origin certainly is a point on this curve, but also you see on the xy plane, the two bisecting angles there, lines there, y is equal to x and y is equal to minus x, going in both directions, they also intersect this curve at every point along there. Okay. Now, for z equal any other constant, then you have a hyperbola, okay? Y squared minus x squared. So sort of another way to express this, when the absolute value of x is less than the absolute value of y, okay, then your z is positive, Okay? So the absolute value of x is less than the absolute value of y. Your z is always positive, as you see here. But when the absolute value of y is less than the absolute value of x, the z is negative. So those will be going down. Okay? So when z is a positive number, you have hyperbole going up, and you see those are those curves. If you're looking in your book, the curves that are opposite each other as you go up, but then in the other quadrants, your hyperbole are going opposite each other in the opposite way, and the z's are going down. Okay, so that's why it's called a hyperbolic, because they form hyperbole in the positive z direction and in the negative z direction. Why it's a paraboloid, if x was equal to 0, you have a parabola, z is equal to y squared. In the yz plane, you have parabole that way, and that's the one that opens upward. Okay. Yeah, the yz plane. Those are the parabola that open upward, or any plane that's parallel to the yz plane. The parabolae are opening upward. Any plane parallel to the xz plane, they're opening downward. And you can see that if you're looking from, say, the seam in the book that way, you can see those parabolae are opening downward. So that's why it's called a hyperbolic paraboloid. Okay, we did some of those before. It's shown there. It says sketch a contour map of that surface. Okay, now when x equals 0, y is equal to 0, z is equal to 0, and they're calling that c is equal to 0, you see in your, if you've got the text, you'll see that forms that cross in the middle. Okay, I will try to draw something similar to it there. Okay, that cross in the middle, that's when c is equal to 0. Okay? Now, and c is your value of z, by the way. Okay? So f of xy is equal to z. That's your c value. So why didn't they leave it as z? I don't know. But when c is positive, and they show in the text, c is equal to 2 would be the first one off of here, and then 4 would be here, and 6 would be here, and 8 would be here, and so on. C is equal to minus 2 would be here, minus 4 would be here, minus 6 would be here, okay, like that. And then they also have the corresponding, for every z is equal to 2 here, z is also equal to 2 there. Minus 2 here, minus 4, minus 6. These are in pairs, these are in pairs, okay. So that's your thing. Now, some of my lines seem to be going backward. They're not. They're all approaching this asymptotically. They're getting closer and closer to that as you go further and further out. So, they go into a little bit more, I don't know, detail. So check your book, okay? Now, that done, let's move on to the top of page 877. That was on the bottom of 876. By the way, Chapter 13, Functions of Several Variables, 13.1, Introduction to Functions of Several Variables. One example of a function of two variables used in economics is the Cobb-Douglas production function. obviously named after some economist named Cobb and another named Douglas, is my guess. Okay, they must have worked collaboratively, or they worked independently but came up with a similar result, about the same time. This function is used as a model to represent the numbers of units produced by varying amounts of labor and capital. If X measures the number, X measures the units of labor, Y measures the units of capital, meaning money, okay, then the number of units produced is f of xy is equal to c x to the a minus c x to the a times y to the, 1 minus a. For a moment I thought that was an alpha, which would be fine. You can name it anything you want to, but it was just my eyes playing trick on me. Where C and A are constants, and A is always between 0 and 1. Okay? Can't be greater than 1 or even equal to 1. Can't be less than 0 or even equal to 0. It's between 0 and 1. Okay. And of course, if A is between 0 and 1, then 1 minus A will also be between 0 and 1. All right. So that leads, Well, that led to example 5, except they don't show example 5. So let me go back and see if I can find, let's use the same slide here, but erase my imperfect drawing. All right. A manufacturer estimates a production function to be f of xy equals 100 x to the 0.6 y to the 0.4. Okay? Man, for some reason, it just got cooler in here. My hands are getting very cold, and usually I'm exactly the opposite. I'm almost too hot. So I don't know if it's cooled off outside and now the AC is working really, really well or what. But anyway, let's move on. Now, I was going to say this about the Cobb-Douglas production function. This function is used as a model to represent the number of units produced by varying amounts of labor and capital. Now, notice the C is just a constant. X is raised to a power that's between 0 and 1. That's your A. And Y is raised to the, I want to say complement. That's not quite the right word. I am so glad that Terrell is here. I'm bored to stiff listening to myself talk. Okay, no problem. My Cal 2 class, Cal 2 class, by the way, 100% attendance today. I come into Cal 3, 0% attendance, but now you're here to break that. So here you are. And Monday, I had 2 people here. Last Wednesday was 0 people here all day.
Wow.
Yeah. Wow. In this class, not the other one. Okay. All right. Let me get things switched around. Since you're here, you may not go back and listen to the first part of this thing. You can if you'd like. It's worth it. But let me just tell you a few there are modifications to my office hours over the next few days. Some are temporary and some will be permanent for the rest of the term. So let me hit the temporary first. Today should be normal as anything is. Tomorrow, normally my office hours on Tuesdays and Thursdays, and they've been all first mini term, from 11:15 until 1:15. That's all I had on Tuesday and Thursday. Okay? Tomorrow, I don't even have that, because as soon as I get out of my trig class around 11:15, I've got to book it over to the Birmingham campus and get a vehicle, because I'm taking my 1:15 class to physical science class on a field trip. Okay, so I will definitely not be on the office around the office for at least an hour. I think it probably will be a little bit more than an hour. So let's just say that I get back at 12:30 or so, plus or minus on that. It's hard to say how long it's going to take to check out the vehicle and what traffic's going to be like getting there and back. So, but probably not much before 12:30, or if it is, it won't be much before, and maybe even after 12:30. So my office hours for tomorrow are around 12:30, plus or minus, until 1:15. Okay, so that's about 45 minutes of office hours tomorrow, and that's all. Because at 1:15, we've got to leave to make the field trip on time. So there's no dawdling around then. So anyway, that's it. Okay. By the way, are you in the first mini-term course?
No.
No. You won't worry about it. Because this is the end of the first mini-term, the end of this week. Okay. Now that also means that the second mini-term begins Monday. Okay. And usually sometime the week after the mini-terms, they ask for midterm progress reports, which means it'd be really good to have some sort of score for everybody. And if I'm not mistaken, I only have one who's turned in a paper and two who have turned in the first test out of the 6 of them. That may be down to 4 now. I don't know. It's actually the first test I had in, that student's not coming anymore. I don't know if they removed her from the roll. I don't know why. I don't know if they're going to put her back in or not. But anyway, so we may not have the 4 people, and one of those can turn in a test already. So half of you I have a score for, and half of you I do not. So yeah, I think you know which you're in. Okay. All right. Now, so try to get something into me. Let's go back to Friday of this week. Okay. Tomorrow, limited office hours because I have to go get a vehicle. Friday, normally my office hours are 8 to 12. However, we've got to go out of town Friday, and we have something we need to be at Friday evening, but we don't know what time. And if they make it fairly early in the evening, then I might have to leave before 12 o'clock, okay? If it's later in the evening, I can leave at 12, but I can't stay past 12 nevertheless. So my office hours on Friday are 8 until somewhere close to 12, but not anything past 12. Usually I'm there after 12, but not tomorrow. Okay, now let's go to next week. Monday should be normal as far as I can tell. But Tuesday, number 1, I have a doctor's appointment, 10:40, and so I doubt if I'll be out of his office at 11, but let's give him benefit of the doubt that I'll get out at 11. Then it'll probably be 11:45 before I get back over here. So I won't be in my office at 11:15, which is normal start time for things. Okay, but starting Tuesday starting Monday is the second mini term, but that's when my class starts, And that class, the second mini-term physical science, rather than starting at 1:15, starts at 3:15, because some of the automotive students are in that, and they don't get out of their block of classes until 3 o'clock. So we don't start the physical science until 3:15, which means I'm here until 7:45 in the evening on Tuesday and Thursday, but that's okay. That's why they pay me the big bucks, right? But so my office hours for the rest of the term will be 11:15 to 3:15. For Tuesday, it'll be whenever I get back from the doctor's office, which probably won't be before 11:45, more likely 12 until 3:15. But then from then on, it should be 11:15 to 3:15. So I got 4 hours office hours on Tuesday and Thursday, which will be a lot better for me, except I stay so late on those nights. So more chances to get to me. All right, too much of that. All right, now what we're looking at, and these, if you're got your text, it's on page 877. It was talking about a Cobb-Douglas production formula, and that's what, in general, it looks like. It's some constant times x to the a, where a is a number between 0 and 1, not 0 and not 1, and then y to the 1 minus a, which would then also be a number between 0 and 1, not 0 nor 1. Okay?
So, how long will you be here today?
Today,
Yes.
I'm here on this campus until 4. I have to leave to go to the Birmingham East campus because I have a class starting there at 4:30, and it goes till 6:30.
Oh.
Yeah. Do you need something? Or?
Well, I was just going to try to get my paper in. I'm done with it. I just
Right.
review it.
Right.
Just to make sure I have everything ready to print out the
Okay.
research page.
Well, if you don't catch me, you can slide it under my door.
Oh.
Okay, because I'll be back in tomorrow morning. I'll pick it up then and get it graded sometime, probably over the weekend, I say, because we're going to be out of town Friday night, Saturday night, and then coming back Sunday morning. So if I don't have any opportunity while I'm out of town, I'll take it with me in case I have some dead time. But if I don't, then I've got Sunday afternoon. Hopefully get it graded. Okay. And tomorrow I have, the class that usually goes till 5:45 probably won't go that late because we've got the field trip and then a few students have, tests to do, either last chapter test or final exams. Most of them did them yesterday, so they wouldn't have to come back after the field trip. But a few chose to do them tomorrow. So I have a feeling they'll be through by 5 o'clock anyway. So from 5 to 6, I'll have office hours then too, so I might be able to get it ready. Maybe. We'll see. Okay. But what I was saying about this Cobb-Douglas production formula, the X represents the number of units, X measures the units of labor, and Y measures the units of capital. Okay? Now, the interesting thing about this is, I guess this is a function of the business itself, but if the importance of X as it goes up, that would be labor. The importance of capital must go down because that's labor, because this would be a higher exponent here, but that would drive this to be a lower exponent. And vice versa, if capital goes up, then the influence of labor goes down, is one way to look at it, which is, I guess, I don't know if that's real life or not, but anyway, they got it. So anyway, here's example 5. Manufacturing estimate, the production function to be that, where X is the number of units of labor, Y is the number of units of capital. Compare the production level when X equal 1,000, that's units of labor, and Y is equal to 500, that's units of capital, with the production levels when X equal 2,000 and y is equal to 1,000. Okay, so obviously you're expanding somehow, both in labor and in capital, doubling labor and doubling capital. Let's see what your production function turns out to be. So your F of 1,500 would be 100 times 1,000 raised to the 0.6 times 500 raised to the 0.4. Okay. So I can't do this in my head. Did you have a calculator? Okay. And I'll trust you to find the proper keys to use on that. Should be pretty self-evident, but I don't know what kind of calculator you have, so I don't know how it's syntax is. So it's 100 times 1,000 raised to the 0.6 power. That's usually a caret key with a 0.6 after it, times 500 caret key or whatever to the 0.4. Okay? It's 0.4, 0.4. Both of those numbers between 0 and 1. Okay, say again.
1,000?
Yeah, this is 100 times 1,000 raised to the 0.6 power times 500 to the 0.4 power. These three things are multiplied. Say again? I can't hear you.
It says give me 16.
Something 16.
Yeah.
What was the something that I missed?
I mean, it just gave me that's the answer. It's giving me.
Okay, something's not. Let me see. Raise that to the y to the x, and then do 0.6 times 500 y to the x. I think that's what they got. Right? So that's 75,786. 75,786. Okay? That would be their production, whatever that stands for. Okay? On the second one, alpha of 2,000, that's the x value, 1,000 the y value, that would be 100 times 2,000 raised to the 0.6 times 1,000 raised to the 0.4. See what that one gives you. 572.
Yeah, round it off.
Yeah. Now, Somehow this doesn't feel too surprising. If you double your labor and double your capital, seems like you should double your production. Okay? Well, what do you get? That's exactly double the production. Okay? Exactly. Okay? So I wasn't sure it was going to come out that smoothly, but that's what it did. Exactly doubling the production. Which I guess should make you feel warm and fuzzy. Okay.
Is it able to change? I know you said labor will be X always? Or?
That's what they said, that X measures the units of labor and Y measures the unit of capital. They don't give you what units those are. That could be labor force itself, or it could be how many people you have working for you, and capital could be how many thousands of dollars you have to spend on it. Well, $500 wouldn't make a lot of sense. $500,000 would be more significant. Okay? So whatever your units are, and that indicates you would be very closely, precisely doubling everything, which I guess is what you would expect. Okay? Now they draw the graphs for various values there. And again, they're calling the C's what normally I would call Z's. That would be the production. And so I guess they have labor on the horizontal axis and capital on the vertical axis. No special reason there. And it shows those curves and picks 2 points. The one at 1,500, the other is at 2,000 and 1,000. So. And your production would be, as indicated there, basically exactly double what it was. Okay. To me, problem doesn't do a lot to convince me of anything, but I guess it's good. Okay. Let's move on from there then to, and that's the one we just did, level surfaces. Okay. Now, just a little bit ago, we did level curves. Well, a level surface is a three-dimensional equal potential type thing, okay? And these get even worse as far as trying to illustrate, because you're now doing a three-dimensional structure on a two-dimensional board, which is never easy. The concept of a level curve can be extended by one dimension to define the level surface. If f is some function of three variables, there's your three dimensions, and c is a constant, then the graph of the equation f of x, y, z is equal to c is a level surface of x. Okay? Now, I don't know if you remember in our quadratic surfaces that we did an elliptic paraboloid of one sheet, that's the bigger one here, two sheets, these are the ones here, and we did a cone, which was intermediate in between the two. This one that there, okay, I guess the outer one here is the two-sheet problem, and that, yeah, I think that's what we're indicating. That's when it's equal to C1. C2 is the cone, and C3 is the distance. So C1 is the elliptic paraboloid of one sheet. The C2 is the cone, and C3 is sorry, the two-sheet problem. Now, as maybe a memory jar here, C1 I think was when it was positive, C2 was when it was 0, the constant is 0, and C3 is when that constant is negative. That's my memory of it. I'm not absolutely certain that's correct. Let's move on from there. So there's a decent illustration of a, three representative values of level surfaces. Okay. All right. Here's example 6. Describe the level surfaces of these. F of x, y, z is 4x squared plus y squared plus z squared. Each level surface has an equation of the form 4x squared plus y squared plus z squared is equal to some constant. Okay? Now, I do not find their illustration there very comforting because that looks too spherical. It's not spherical, but it's awfully close. And one of those dimensions should be 4 times the others. And I just don't see a surface that would qualify that way. So, anyway. So, how do we describe the level surfaces? Well, instead of this, we put in numbers. Okay? And I'm going to pick a number that will be fairly convenient. I'm going to pick the number 4. So if we have 4 is equal to 4x squared plus y squared plus z squared, and then divide everything by 4, we have 1 is equal to x squared plus y squared over 2 squared plus z squared over 2 squared. Okay. Z's and 2's look suspiciously like each other, but they're not. So this is over 1 squared. And maybe this is why the figure in the book doesn't look that great, because it's the x-axis that's squished, and since it's coming out of the page, you don't really see it that much. But it comes 1 on x for every 2. Oh my goodness. Be still my heart. Okay. What's that?
Huh?
These are pre-cal algebra. No, I haven't had a chance to grade them. I gave 2 more tests yesterday to a class that is finishing a mini term. I had to get those graded first because I have to get those in. Okay. Did you need to finish yours or?
Oh, no, I finished one.
You did, okay.
I just want to know if you're going to keep me posted.
Yeah, it's going to be a while before they get posted because I've got to finish grading them first, then I'll post them. So.
And then you got to go through the whole posting thing.
Yeah. So, sorry, I'll work on them, but.
No need to apologize. Okay.
Yeah.
All right.
Okay.
I'll see you tomorrow.
All right. And Justin came in. I thought at first that he was someone who had from the class. I hadn't seen him so long, I couldn't remember he was in the class, and I realized that he was in my other class. Okay. So what is this one? Any idea what that would be? All the signs are positive. Hyperbolic is an ellipsoid. Everything is an ellipse here. That's constant, that's an ellipse, that constant, that's an ellipse, that constant, that's an ellipse. In every dimension. Okay. In fact, that last one was a circle in X and Y and Z. That's a circle that way, but ellipse is the other two ways. Okay, so that's an ellipsoid. Now, I don't believe, in fact, I'm absolutely certain of it. Your F can never be negative, right? If X, Y, and Z are all three zeros, then there could be zero, okay? But if X, Y, and Z are anything else other than zero, or at least one of them is anything else other than zero, this whole thing is positive. It can't be negative. So your F here is never negative. So don't plug in a negative number. It can't happen, okay? You could plug in a zero, then it would be the point x, y, x equals 0, y is equals 0, z is equals 0, and your F is 0, okay? Or however fourth space you plot that. Then for any positive F, this is going to be some ellipsoid. Whatever your F is, divide by it, and you get your radius of that ellipse, okay? So, of that dimension. So those are going to be series of concentric ellipses, okay? Does that make sense? Okay. Now, we divided, or I divided by 4. You could have divided by 16. You could have divided by anything that has a common factor of 4 and 1, you know, so anyway.
But how did you get the 2 squared?
The what?
The 2 squared, where 1 equals x squared plus y squared over 2 squared.
One more time.
Where when you have
Yeah. Okay. This just became 1. All right. 4 over 4 is 1. So that's your x squared over 1 squared. Then this is y squared over 4, which 4 is 2 squared. All right. And z, this is 4 there. You divide it by 4, and that is 2 squared. All right. I just did it that way. That means you go plus or minus 2 on the y-axis, plus or minus 2 on the z-axis, and plus or minus 1 on the x-axis, and that gives you your the limits of your ellipse. Plus or minus 1 on x, plus or minus 2 on y, plus or minus 2 on z. And then the ellipse is that figure that connects all this. Okay. Closed figure, by the way. So that's just a series of concentric ellipses. Now, that's really all they do. Well, let's see. They'll draw you a picture, which is going to be far better than my waving my arms. Okay, each level surface has an equation of the form 4x squared plus y squared plus z squared is equal to some number c. I pointed out to you, c could be 0, and then it's a trivial solution, 0, 0, 0. Okay, or it could be any other positive number. It could never be negative, because there's no way those things squared can ever be negative. Okay. So that should, so the level surfaces are ellipsoids whose cross sections parallel the to the XZ planes or circles. Like I said, that forms a circle. These form ellipses. Okay. So the YZ plane, the cross section are actually circles, and that's why, in many senses, the this did look more like spheres than it did ellipses because you see the YZ plane almost as the plane of the page, not quite, but close to it. And those are circular or near circular. Okay. Now, as C increases, the radii of the circular cross sections increase according to the square root of C. But why do they only talk about the circular cross sections? All of them do. For example, the level surfaces corresponding to values C equals 0, C equals 4, and C equals 16 are shown, or they say are as follows. So when you put C equals 0, your only other point is the origin, okay, in 4 space even, okay, and we did the one where it's equal to dividing by 4, and then they showed the one dividing by 16, okay. All right, now what you probably can't, well, here it is. C is equal to 0 is only the origin. Because if C is equal to 0, X, Y, and Z all have to be exactly 0. None of them can be anything but 0. So that's just that point right in the center. C is equal to 4 would be where the X, Y, the cross section is a circle, and the YZ plane, the cross section is a circle. The XY cross section would be an ellipse, and the YZ cross section would be an ellipse also. In fact, those two ellipses are identical in scope and everything to each other, so that's what gives it so much symmetry. If you divide it by 16, if you set this equal to 16, C is equal to 16, divided by that, now you have a radius of 2 on the x-axis, not radius. It goes up plus or minus 2 on the x-axis, plus or minus 4 on the y and z. So it's just a bigger shape of basically the same thing. But again, an ellipse sort. Okay. All right. If the function represents the temperature at a point x, y, z, then the level surfaces are shown in figure 1315 that we just had there, that figure there. These would be called isothermal surfaces, okay? At the origins is one temperature only. That's only 1 point. But here, out here, every point on here would be the same temperature, whatever that C was that produced it 4. Out here, it would be 16, okay? So those would be your isothermal surfaces. Okay. And frankly, if you're in a room that with absolutely no wind currents, I don't know how you would avoid hot air rising, but if you could avoid that, and you had a point source that's heating right there, then the C would be that point source that's heating. And then after a while, this circle would all be at one, not circle, the ellipsoid would be at one temperature, this one would be at one temperature. And the longer you heat, the isothermal surfaces are getting bigger and bigger and bigger because they're moving further away. Okay. Now they have a thing on computer graphics. I think what the point is, let the computer do the drawing for you and you don't have to mess with it. So I'm going to go through this hopefully pretty quickly. I'll try to anyway. Problem of sketching the graph of a surface in space can be simplified by using a computer. Thank you very much. Although there are several types of three-dimensional graphing utilities, most use some form of the trace analysis given in the illustration and illusion of 3 dimensions. To use such a graphing utility, you usually need to enter the equation of the surface and the region of the xy plane over which the surface is to be plotted. You might also need to enter the number of traces to be taken. This is not very specific. Okay. For instance, to graph this surface, f of xy is equal to x squared plus y squared times e to the 1 minus y squared minus x squared. Okay. And your bounds on x will be from minus 3 to 3, bounds on y from minus 3 to 3. And, all right. Since two of you have come in since I said it, I guess I need to say it again. If the fourth person is listening to it on the thing, he's heard this now 3 times. Or if he comes in, no, Daniel won't be here today because he's working today. There are some changes coming up for my office hours. Some are temporary and some are permanent. Let me hit what they are. Tomorrow, normally office hours on Tuesday, Thursday for the first mini term have been 11:15 to 1:15. However, tomorrow I'm taking my physical science class on a field trip, so I've got to, as soon as I get out of the class that ends at 11:15, I've got to get over to the Birmingham campus, get a vehicle that I've already reserved over there to bring back here so I can drive people to the field trip. Okay? So I will not be in the office from 11:15 to 1:15. It will be more likely, and this is just a guess, 12:30-ish to 1:15. I might get back before 12:30, or it might be later than 12:30, but it won't be more than about 45 minutes tomorrow. But on the positive side of that, that class will not go until 5:45 like it normally does, because all they've got to do, we've got to do the field trip. Hopefully we'll be back here by 4, and then a few of them have to take either last chapter test or the final exam. Okay, some have taken most of them have taken the last chapter test. I think there's only probably 2 or 3 people who haven't taken the last chapter test, and then maybe only 4 or 5 who haven't taken the final exam. Because I gave them the option of, if you want to go home from the field trip, you can, but you'll need to take your test early. And most of them chose to do that in case they didn't want to go. So, anyway, so what I'm getting at is I don't know what time I'll be back in the office. Probably, easily, we'll be back there by 5 o'clock. So there will be some office hours at the end of the day, even though I won't have them at the beginning of the day. But that's just temporary. That's just because of the field trip tomorrow. On Friday, I have to leave town, and I have to be somewhere in Atlanta sometime Friday afternoon. Now, I haven't heard from anyone exactly what time. If it's late, say in the evening or something, I probably can leave at 12. But if it's earlier in the day, I'm going to have to leave a little earlier than 12. Normally on Fridays, I'm there from 8 to 12, and usually there after 12. But on Friday, I know I have to leave no later than 12, and it may actually be earlier than 12. So that's a minor change there. Okay, Monday of next week should be normal. Okay, Tuesday of next week, there's a temporary thing and a permanent thing. The temporary thing is I've got a doctor's appointment Tuesday at 10:40. Normally my office hours start at 11:15. With the doctor's appointment at 10:40, I'm almost guarantee you I will not be out of his office before 11 o'clock. He never been through that quickly, I don't think. So even if I left at 11, I won't be back here until around 11:45. So I'm going to lose at least half an hour and maybe even longer. But on the positive side for office hours is because that second mini-term, and by the way, are either of you in the first mini-term class? No? You are? Okay, have you done your student course evaluation for it? Okay, good. Did you say a PE? Okay. Someone this morning was like, do you have to do it for a PE class? I thought, I believe so. Yeah. All right. But second mini-term, I have a first mini-term class. It starts Tuesday, Thursday at 1:15. That's what that is. Second mini-term class, however, because the automotive students are in it, several of them are, they don't get out of their block class, which goes 1 to 3, until 3 o'clock. So that means I can't start my class until no earlier than 3:15. So that means my office hours from now on, next week will be, and for the rest of the term will be 11:15 to 3:15, full 4 hours of office hours rather than 2, but that means I'll be staying here until 7:45 at night rather than 5:45. So anyway, those are the changes coming up next week. 3 of those changes are temporary. 1 of them's good for the rest of the term after tomorrow. Okay, so these were the limitations. Now, why is Z always, oh, wait. I'm sorry. This is a new one here. Here's to graph this surface, you might choose the following bounds for X, Y, and Z. And X and Y, you choose whatever you want to, but they can be positive or negative. So let's just choose plus, from -3 to +3 for X's and Y. Z, which the Y represents now, that Z, if you'll notice, X squared is always positive, Y squared is always positive, X squared plus Y squared is always positive. Now, they could be 0, for sure. That's why 0 is included here, if X and Y are both 0s. And then your E is always positive, okay? So, wow, you've got everything positive, so your Z is always going to be between 0 and let's see if 3 makes sense there. You have the maximum Z when, this is just a guess now, you have a minimum X and Y. Okay? So let's say, and they can't be 0 because then the whole thing would be correct. So that's going to be a lot harder to tell. I don't know why they picked up this Z here. Because if that's if you chose 3, the max here, either plus or minus 3, that would be 9 plus 9 is 18 times e to the 1 minus 9 minus 9. That would be e to the minus 17. E to the minus 17 is awfully close to 0. So, I don't know. You'd have to do some manipulation there to see why they chose Z going up to 3. Okay. But here is a computer-generated graph of that surface. And see, I don't think the Z even gets up to 3, but they just chose that to be the range. Okay? This, of course, would be the line X equals 3, Y is equal to 3, X equals -3, that means Y is equal to -3. Z never gets up to 3, I don't think. Okay? So this is a computer-generated graph of that surface using 26 traces taken parallel to the XZ plane. Okay? Here's the XZ plane, and these are the traces parallel to that. mean, they're just showing it to you. I can't think of much to expound on that. I mean, there's just not much you can say about it, okay? So, and notice what does happen. Like I said, your max for Z is something in between 0 and 3, or 0 and minus 3 in every case. And it's something that looks like closer to the 0 side than the positive side. You know, something beyond that value, because by the time you get to 3s, they're almost flat again. Okay. That is, it begins by plotting the traces in the foreground. Okay. They're talking here about a hidden line routine. If it starts tracing here, when x equals 3, y is going from minus 3 to plus 3, plug those values in, and you're going to get almost nothing. Like I said, that is going to be you can put different things in there. Even when y is equal to 0, that would be right here, you have 9 times e to the minus 8. That's going to be a very small number. Okay, so, and then any other y's you put in are going to be even closer to 0. Okay, you do the same thing with the other. But you plot each of these. Okay, they've gotten 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, maybe 27. Okay, I don't know, something like that. Yeah, but anyway, we got those equally spaced, and then you plot these when x equals 3, x equals 2.7 to 8, 2.4, you know, they count backwards from there, and then you'll see things start increasing, decreasing, increasing. So that's the shape you get. Now, what they mean here, the hidden line routine, they don't describe it except that saying there's some places here you can't see where this line goes. So it just traces along another line. Okay, I guess. I don't know how they do that, so can't begin to tell you. But you just pick one of your axes and just choose lines parallel to that, x equal, like you said, 3, 2.5, 2. Whatever, all the way back to -3, equal spaced. Okay, that is, it begins by plotting the traces in the foreground, those corresponding to the largest x values. Then as each new trace is plotted, the program determines whether all or only part of the next trace should be shown. In other words, when it gets to doing some things in the background, you don't want it to be too confusing. The graphs on the next slide show a variety of surfaces that were plotted by a computer. Yay, okay. If you have access to a computer drawing program, use it to reproduce these surfaces. I don't. If you do, knock yourself out. Now, what they've also done here is rotate it. This is one graph here, okay? Well, this is not the same as the one we had before, but it's a different graph. Sort of the same thing. Before it was just x squared plus y squared. Now it's 2 minus y squared plus x squared, so it's a very different first function. And then the second function was 1 minus x squared minus y squared. Now it's 1 minus x squared minus y squared over 4. Okay? Now what they've done also is rotate these around. Now notice your x-axis here, y there, z there. You have to have a right-hand rule. Point your fingers in the direction of the x-axis of your right hand, twist them to point to the positive y-axis, you see it's going to point upward. So this is one that's sort of what they call an isometric view. Now they've taken that and twisted it twisted it this way, just a little bit, and now you have your x-axis moved up a little bit and y moved down a little bit. You know, you twisted it counterclockwise. So what was coming down here is now coming down right at you. Okay, twist it even more. In other words, about 270 degrees from where it is. In other words, the x twists all the way to here, the y twists all the way to there. So you have more of that type of thing. In fact, it's probably 270 from here, or twisting backward 90 degrees from here. Okay. And now you see what was on the backside there here, and you can't see some of this activity on the front side. You see a little bit of it maybe right there. Okay. Again, without having the computer programs to play with, it's a lot of blah, blah, blah. Okay, so there's the first one. The next one was one like this. Now, go back to this one. Notice here they did something else they hadn't done before. You went back in X's and got those things, but then they also did traces for Y. That's why you have the checkerboard pattern here that you didn't have before. And you have it there as well. Okay? This one is illustrating that. Here you have just the traces along the x-axis, different values for x that are dipping here and going up there. But your y's, they put those in like this, and then they dip here and go up here. So you've got that going on too. Maybe that's a little easier to visualize. I'm not certain that it is, but it, I guess, could be. Okay. Now this function happens to be this one. That when x's are positive, the whole thing is negative. Okay. And when x's are negative, the whole thing is positive. So here's where it's negative here, here's where it's positive there. Okay. Now, they talked about the level curves for this drawing. Now here's the problem. You can't tell which are raised and which are depressed. These over here are obviously depressed. And let's see, get my x-y axis oriented properly here. Sort of hard to say. This positive x here is the one going here. The negative x is the one going back here. The positive y is the one coming out here, and the negative y is the one going back there. Okay. This is a raised peak. That's that point right there. Here is your depression. That's there right there. And since you don't have any numbers on them, you don't have any color coding indicating whether it's positive or negative, that just looks like two owl eyes or something like that. But they're not. They're very different. These are depressed values. Let's see. These are your depressed values. These are your elevated values. Okay? So the level curves are fairly uniform there. Now, you don't see anything look like it here because these are parallel, perpendicular to the axes here. What you'd have to have there would be ones that are isothermal or iso something to be able to pick those out. And this just doesn't show it. Okay. Here is another one. This is sine x, sine y. Oh, these are three different functions. Sorry. And they're double, what do they call them? Double traces, I guess. That's what you call them, double level curves. This is just sine x, sine y. And you can almost see the undulation that you would expect from a trigonometric function. But some of them are twice as tall, maximum 1, maximum 1, so we'll never get beyond plus or minus 1. Okay. Okay. Your maximum would be when x is equal to pi halves and y is equal to pi halves 2. Then you I can't, except for the fact that they oscillate like a sine or a cosine, can't say too much more about that. This one, minus 1 over the square root of this, obviously this is always negative, can't be positive, because that's positive, and this is always positive. So, and you put a minus sign in front of it, it's always negative. So this is something, for the life of me, it looks like that is above the xy plane. And it couldn't be. It has to be a yay. So I think the xy plane is, this makes it look like this is on top of it. It's not. The plane is out here, and this is the very maximum. They're coming asymptotically approaching those values there. Okay. Not there. Okay. Here's one a bit more involved. The f of xy is equal to this thing over the square root of that thing. And certainly when x's and y's are large enough, then these things go negative, okay? Because your denominator is a square root, which means a principal square root, positive square root, and the number in here is an absolute value. It would have to be, otherwise x's and y's both have to simultaneously be less than 1, okay? In fact, less than that, I think. So, anyway, another way of looking at that. Oh, am I going to generate any of these? No. I doubt if y'all will, but if you do, that's how you do it. Okay, I'm glad to be through with that. And frankly, on that one, I can't think there's... Oh, yeah. Okay. 5 and 7 you can do. They're both at Calc Chat. You can do any of the odds 9 through 19. They're all at Calc Chat. 9's at Calc View. I think you can do any of the odds 21 to 31. They're all at Calc Chat. 23 to Calc View. There's a think about it. You can think about it if you want to. Number 33, it should be at Calc Chat. There's a sketching one. You can do it if you'd like. These shouldn't be too difficult. 35 to 41. They're all at Calc Chat. Sometimes sketching is just really difficult, so do them if you'd like, and certainly look at Calc Chat and Calc View to see how they do it. And then 43 and 45 are using the goodness gracious, I'm going blank on the name. It's the computer graphing device. What do they call it? Utility, graphing utility. Okay, so it's either 43 or 45. And then 47 to 51, I would try to do them all. Okay, that's not right. 47 to 50. 47, 48, 49, and 50. There's 4 equations there. Match the figure with the... I'm trying to see them now. Oh. All right. Oh, I got it. 47 is the equation with the drawing, 48, 49, and 50. okay, then you match the A, B, C, D with whichever one of those graphs it is, okay? That's just for funsies, and I wish they at least had a color indicating whether it was going positive or negative. Okay. Okay. I was going to do one of those for you. Well, work on them. If you have any questions, we'll do it. I don't think it's worth taking class time to do it. Though I'm still tempted. Let me see. It looks like to me that 47 is probably your C graph. But I'll let you play with that. We won't do any more of this. Then do any of the odds 51 to 57. They're all at CalcChat. 51 is at CalcView. And by the way, 47, 49 should be at CalcChat. 59 and 61, both at CalcChat. I'll let you decide to do one or more. Exploring concepts, again, you decide. 63 or 65, they should be at CalcChat. You can check that out. 40 or 67, you should be able to do. It's at CalcChat. 69 is an application problem. It's at CalcChat. 71 and 73. Oh, any of the odds 71 to 75. Again, these are up to you because sketching these things are sometimes a pain in the neck, but 71 to 75. 71 is at CalcView. There's a forestry problem there. I think I mentioned something there. The Doyle log rule, okay. I don't know if that's the LOG with forestry or LOG natural logarithm, or not common logarithm, but whatever. There's one more application problem, temperature distribution. 79 is at CalcChat. 81 is at both CalcChat and CalcView. And then there's a Cobbs-Douglas production function at 83. And then the rest of them are pretty see, 85 through 89, you can pick one or more of those to do. They should be at CalcChat. 91 and 93 are true false, so if you want to try those, they should be at CalcChat. Goodness gracious, let's be through with that. Let's move on to 13.2. We've got, what, 6 minutes to go, so let's get as far as we can here. Okay, we'll go from current slide. Okay. All right, limits and continuity. I hope we can sort of breeze through this fairly quickly. The objectives here are to understand the definition of a neighborhood in a plane. We've already been talking about it, we just haven't called it a neighborhood. We called it a region in a plane. We called it D. I can't remember exactly what that stood for, except just domain. We'll understand and use the definition of a limit of a function of two variables, extend the concept of continuity of a function to two variables, and we'll extend the concept of continuity to a function of three variables. Okay? So let's talk first about Feeling good in the neighborhoods. Okay. Using the formula for the distance between 2 points xy and x0, y0. Now, that's a little bit of a bizarre thing because you usually think of xy as being a nondescript point, not a specific point, just representing a point, where this represents a specific point. Okay? You can define the delta neighborhood. Now, if you're beginning to wonder why they call it the delta neighborhood, think back to our early working with limits. Let epsilon be greater than 0. There is a delta such that, delta describes the domain part. Hey, now we're talking about a neighborhood delta. Okay. About that point x0, y0 to be a disk, so the delta can stand for disk too, centered at x0, y0 with a radius delta being something greater than 0. Okay? And we always said there is a delta greater than 0. It comes into more importance perhaps now. A little more value. It's not just a window on the x-axis, it's a window in the xy plane. So your set of all points xy such that the square root of x minus x0 squared plus y minus y0 squared is less than that delta that's greater than 0. Okay? So that defines your neighborhood, your disk. Now this one's called an open disk. Anyone want to make a guess of why it's called an open disk? It's strictly less than, meaning it's all the points in here that are less than that delta, not on the delta. If you included the delta and had less than or equal to, that would be a closed disk, because then you would count the points there. This one said less than, so that's an open disk. Does it matter? Not really most of the time. There may be certain circumstances when it does. It does really matter. It's something we're going to do later. We're going to let some point get close to, but can't touch that. Now, if that was part of the domain, then it could be on the edge, and that can't happen. Now it can be near the edge, but you can always find the radius around it that you can still be in the disk. If you were on the edge, you couldn't do that. So there is that reason to have an open disk. Okay, when that formula contains less than inequality, so like I just said, the disk is called open when it contains less than or equal to, it's called closed. I didn't know they were going to say this. This corresponds to the use of less than or less than or equal to define open and closed intervals, just like we did before. Closed interval, open interval. Okay. So let the region R, now we're going to call it a region, R, be a set of points in the plane. A point x0, y0 in that R is an interior point of R if there exists a delta neighborhood around the point x0, y0 that lies entirely in R, as shown in this figure. So if there's a point that you can put a delta neighborhood around, that's always going to be a circle, okay? And if that circle doesn't intersect the outside here, the boundary, then it's an interior point. If it does intersect the boundary, that means that point is on the boundary. Because anywhere else, no matter how close you get to the boundary, as long as you're not touching it, you can have your delta minuscule enough, you can draw one of those very small discs around it. So it's a boundary point if it's on the boundary, interior point if it doesn't touch the boundary. Okay? So that's that. Now, this is your overall region R, what you're dealing with. This is your immediate domain element, I guess you would call it. If every point in R is an interior point, then R is an open region. In other words, it doesn't have a boundary that's part of it. The boundary is not part of it, okay? It's just like the boundary of the circle, okay? Okay, the point x0, y0 is a boundary point of R if every open disk centered at x0, y0 contains points inside and outside R. If R contains all of its boundary points, then it's a closed region. Blah, 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 right? Okay. How are we doing? About over? So let's start next time. By the way, before we move on here, there is a featured mathematician, Sonia Kovalevsky, I think is how you pronounce her name. She was, much of the terminology to define limits and continuity were introduced by a German mathematician called Weierstrass, okay? And he would be someone you could do. He's the father of modern analysis. But he was also a very gifted teacher, and one of his best-known students was a Russian mathematician, Sonia Kovalevsky, who applied many of his techniques to mathematical physics and became the first woman to gain acceptance as a research mathematician. Pretty incredible. So if you choose to write on her, good paper topic. All right, so we will pick up next time limit of a function of two variables. That's the top of page 885. All right, got a test in.
Scared.
Good deal. Huh?
Scared about that.
You scared about it? Don't be. Though I will say this, it was a tougher test than I thought it was going to be. Yeah. Yeah. Now, actually, the last four turned out to be the easiest ones, I thought. Well, I sort of knew that when I was typing them, but I just couldn't think of any other way to do it.